Good evening, ma'am.
Yes, good evening, everyone. Today, we are going to revise week 3 and week 4. Right. This session is not recorded, but this session is being live streamed. So you can find the YouTube link in the calendar. Okay. So in week 1 and week 2, what we have seen so far is we have seen what is PCA, and we saw that it's basically the dimensionality reduction technique where we studied these three things, like how to transform the original feature space into lower dimension, what the orthogonal features, and we also looked at what is called the kernel PCA. So in this week 3 and week 4, what we have seen, what we are going to see is the clustering and some estimation problem. So when we talk about clustering, we are going to look at a very important powerful algorithm, which is K-means algorithm and Lloyd's algorithm. And we'll also see some initialization technique, a different kind of special initialization technique, which we call it as K-means plus plus. Right. So we'll start now with V3. So clustering is nothing but a unsupervised learning algorithm. And what we had seen is now our goal is to like whatever data set we have, we want to see if there is some underlying structure in the data set. That was our goal. If there is some underlying structure in the data set, we want to capture those, we want to understand those structure. So this process of doing it is what we call as clustering. So the thing is that let's say if you have a general setup. So let's say if you have a data set with n points, right? You have x1, x2 up to xn, and you want to partition your data set in some k different partitions. So what we are saying is, let's say this is my one partition, this is my second partition, and let's say this is my some k partition. Now I want to, I have these data points available to us. And what are these data points? These data points are x1, x2, so on till xn. So what I want to do now is I want to take each data point and would like to put these data point in one of the cluster, right? In one of the partition. So x1 can either go to the first cluster or can go to the second cluster, it can go to the third cluster. Similarly, x2 can go to any three of these clusters, right? Any of the three partitions, x2 can go. So here what we saw is we have k different partitions for the data set. I mean, our goal is to put these data set into k different partitions. And I know that for every data point, I have k different possibility, right? So for x1, I have k different possibility. For x2, I have k different possibility. So on till xn, I have k different possibilities. So every data point has some k different possibilities. So how many configurations do we think are possible? Because I have n different data points and I want to put into k different clusters. So it would be nothing but k to the power n, right? So number of configurations that are possible is k to the power n, because each data point has Because when we are saying, let's say first data point, then I have k, second data point, then I have k, right? And we have some k data points. So this is nothing but k to the power n configurations that are possible. But this is too many possibilities, right? I mean, in case my data set is quite large, if my n is very large as compared to d, then what happens? If n is very large, okay, if n is very large, then in that case, even if, let's say, I want to partition my data set into just two clusters or three cluster and some n is some 10,000, then this value is just way too big, right? So we cannot go and find out all the configurations and then look at which is the best. So that is not a great idea because there are too many possibilities and it is very difficult to solve this problem. So to all right, I will move further. So what we want is we want to know what we saw is some we need some k different partition, right? I mean, k different partitions we want for the data set. And we said that we have k to the power n different possibilities. Now, these possibilities, I mean, it can be any way. Let's say all the data points are going into one, or each data point is in each individual cluster. I mean, there are many ways, which is k to the power n ways. Now, how do we identify like which partition is good? For example, like if I have, let's say, just 5 data points, x1, x2, x3, x4, and x5, and I just have two clusters. Let's say I have one cluster and I have second cluster. Now, one possibility is that I can put my data point x1, x2 in the first cluster and the remaining 3 data point in the second cluster. This is one way to do it. Other way to do it is, let's say I put my x2 and x4 in the first cluster, or x5, x1, 3 in the second cluster. This is also one way to do it. So let's say if you have certain partitions given, how do you decide if this is a good partition? So you will need a metric that will, in a way, quantify the goodness of this partition, right? So intuitively, we want something such that, like, every data point, in a sense, they are in every cluster, each and every cluster, they are more homogeneous, right? We want all the data points to be spread in a cluster uniformly, in a sense. And you want a partition such that any data point which is there in a particular partition should be more closer to that center instead of the other center. So in a way, what we want is we want to maximize. So not maximize, sorry, minimize. We want to minimize the distance of each of the data point. So this is the L2 norm. So I want to minimize the distance of xi's, each of the xi's, from mu of zi. Okay. So I want this to be as small as possible. We want to minimize this over my z1, z2, so on till zn. So what is this x's and zn? So what we are saying is that if we have the n data point, x1, x2, so on till xn, then each data point will have a particular cluster indicator. So x1 will have z1, x2 will have z2, and xn will have zn, right? And each of these zi should belong to 1 to so on till k. Why is that? Because these zi's, I mean z1, z2 up to zn, these are just the cluster indicators. Because for any data point I take, I want to know which cluster does it go to. So if I just look at this example, let's say I am interested in this example. So what happens? So I have two clusters here. This is cluster 1 and cluster 2. So what I'm saying is that my x1 cluster x1, sorry, data point x1 goes to cluster 1. So um, so 1 x1 goes to 1, x2 would go to 1, x3, x4, x5 would go to 2, right? So this one is basically what Z1. This one is basically Z2. This 2 is X3, Z3, and these two are Z4 and Z5. So for every data point is associated with some cluster indicator. So that is why we are saying X1, X2, X2, Xn is associated with other cluster indicators Z1, Z2, and so on till Zn. But each of these Zs will always belong to 1 to k, because these are the number of partitions that I want for my data set. Okay. Then, okay. So what I was saying, we want to minimize this distance, and we want to minimize it over these Zis. So the objective function that I'm interested in, so what is my objective function? The objective function that I get of Z1, Z2, so on till Zn is nothing but sum over xi minus mu zi square I varying from 1 to n, right? And what is this mu zi? So mu I, yes. Um, wait. So we have mu zi, I mean, what is this mu zi? So mu zi are the mean of uh, mean of the cluster in which you have this data point xi. So if let's say I have this cluster, then I will have mu1 and mu2, right? Mu1 is the mean for the cluster 1. This would be mean for cluster 1, and mu2 would be mean for cluster 2. So when we say mean of cluster 1 and mean of cluster 2, what do we mean? So if this is a cluster that I have, then the mean of this cluster would be what? You will add these two. I mean, so this cluster has two data points, x1 and x2. So you will take the mean of these two data points, and that would be your mu1. If I'm saying my cluster 2 mean, that is mu2, it means all the data points that you have in your cluster 2, you will take the mean of that cluster, right? You mean take the mean of those data points. For example, let's say my x1 was 1 and x2 was 3. And the second cluster, let's say my x3 is 4, 2, and 3. Okay. So what happens here? So if I have to find mu1 here, mu1 would be mean of the cluster 1. So mean of cluster 1 is 3 plus 1 divided by 2, right? Which is 2. What is mu2? Mu2 will be mean of the cluster 2. So mean of the cluster 2 is 4 plus 2 plus 3 divided by 3, right? And this is 3. So my mu1 will be 2 and my mu2 will be 3. So just in case if you have to find for some question, you have to find the cluster means, this is how you do. So any data point which you have in that cluster, you take the mean for those data point, and that would be your cluster mean. All right. So how do we write this? How do we write this term? This term. How do we? I mean, so mathematically, what we can write mu k as. So mu k. How to define any cluster mean? We find the cluster mean in such a way that you take the sum. I mean, you take all the data point that you have in that cluster. So let's say I have the data point xi. Now, since it is restricted to this cluster K, right? So this is restricted to the cluster K, then in that case, I will need the points, I will need those points that are there in cluster K. So that is why we define this indicator function, which is defined as indicator of Z is equal to K, where I is varying from 1 to n. So as we had seen this before, that what is this? How is this defined? So this will be defined as if you have indicator of zeta is equal to k. Right. This is what I want. So if your zeta is equal to k, then you will give it 1 here. Otherwise, it will be 0. I mean, whatever is there inside the indicator function, if that holds, if zeta is equal to k, right, then I will call it as 1. Otherwise, I will call it as 0. Otherwise, right. So mean of mu k is nothing but sum over xi times indicator of zeta is equal to k divided by sum over indicator of zeta is equal to k, because this will give you the points which are there in um, the number of points for which the number of points which are there in that cluster K, right? So this is, I mean, whatever we have discussed it over here. I mean, taking a small example, what we have said, this is exactly the same way. I mean, mathematically, this is how you write it, right?
Excuse me, ma'am.
Yes.
Sorry, I joined the session a bit
Yeah.
late. Ma'am, can you tell me what is ZI here? Please, is there a formula, or is that the data points which are you equating to K?
Um. So no. So okay. So Zi's are here. So you have n data points, right? You have data point
Yes, ma'am.
x1, x2 up to xn. So what we are saying is like every data point will be assigned to some particular cluster, right?
Cluster. Yes, ma'am.
So x1 can be in the first cluster, x2 can be in the second
Second
cluster.
cluster.
So if in case my first data point is in cluster 1, then I will say my z1 is 1.
Okay,
And
ma'am.
if my second cluster, it's like that.
Understood. Thank you.
Okay. All right. So this is how you find the mean of any cluster. And our objective is basically to minimize this distance. So what is this doing? What is this doing is that uh, you want the in any particular cluster, you want those data points which are more closer to the mean of that particular cluster, right? So whatever assignment makes it the minimum, that is what the ideal clusters are, ideal cluster indicators are. So for this, like as we said that my original problem, which was like putting my n data points in k different cluster, this has too many possibilities. So it is not solvable. I mean, we call it as NP-hard problem. So to solve that problem, we are going to introduce a very important algorithm here, which is called Lloyd algorithm, or sometimes it is also called the k-means algorithm. So in Lloyd algorithm, these are the steps that we're going to use. So what does it say? So in Lloyd's algorithm, our goal is to find that partition which is the most ideal. So your goal is to partition the data set into k different cluster. Our original problem, what we had in this strategy, you have the data set, you have k different cluster, and now you want to partition the data set. But what is the best way to do it? What is something that is, I mean, how using Lloyd's algorithm, we will see how can you achieve this. So the first thing that you do is you choose k different cluster means randomly. Okay, so this is called the initialization step. So in the initialization step, you are choosing random k different means because you have k different cluster and you want to choose k different cluster means randomly. Now assign each data point to one of the k cluster, right? So since you have randomly chosen k different cluster mean, so now your goal is to, so let's say I choose, I have n data points. From those n data points, I choose some k different cluster means. I'm choosing cluster means, okay? So once I've chosen my cluster mean, my next goal is to put those to put all the data points in one of those clusters. Okay? So let's say if I have if my k is 3, okay, if my k is 3, I randomly chose three different cluster means. So this is my new one, this is my new two, and this is my new three. Now I have some n different data points. I have some n different data points, and now I want to put all these different data point into one of these cluster. So to do that, what we can do, we will take each data point. So let's say this is my data point. I would want to find the distance. So if this is my xi, I would want to calculate the distance of my xi with mu1, with mu2, and with mu3. Okay. This is one example where I've taken k to be 3. So whatever distance is minimum, my xi will take that cluster. So in this case, visually as you can see, that my xi data point is closest to mu1. So I will assign x1 to xi to mu1. Let's say I have some other data point, which is, let's say here. Let's say this is my xj. Now again, I will have to assign this xj to one of the cluster. So we will calculate its distance from each of mu1, mu2, and mu3. So now here what we can see is my xj is more closer to mu2. So I will assign xj to mu2. In the same fashion, you can take each and every data point and you can calculate the distance of each data point from each of the cluster means that you have chosen. So that is my first step. And then whatever distance is minimum for every data point, you will assign that data point to that cluster. That is my step 2. This is what we're doing. Then once, let's say I have some assignment. So I have three means. Let's say I have assigned some data point to these 3 clusters. So now I have some data points in each of this cluster. So we don't know whether this is the most ideal one. So what do we do is I calculate the cluster mean again. All right. Because once you have put in the data points, you have put in the data points in each of these cluster, now your cluster mean will change, right? Initially, you had randomly taken this cluster mean, but once you have put in the data points in each of the cluster, depending on which data point is more closer to which of the cluster mean, then your assignment again changes for each of the clusters. So now every cluster will have some data points. Again, what you will do is, again, you will calculate now mu1 dash, mu2 dash, and mu3 dash. This will be different from your initial means that you had randomly chosen. And once you had calculated, so that is my step 3. So what I will do is I will calculate my cluster mean again, and I will calculate the mean of the data point that belongs to that cluster, and that will give me the cluster mean. So once I do that, I will repeat these two steps, step 2 and step 3, until convergence. So until convergence means when I reach to a when I reach to a certain assignment such that every data point is the closest to its own cluster mean. So once that happens, I will say my algorithm has converged. So let's say if this is the new clusters that I found, new cluster means that I found, then again I should go ahead and find the distance. Again, I will have all data points in each of these clusters. Now, again, I will take all these data points and calculate its distance, calculate the distances from the new cluster means that I have found. So even if one of the data point which was not happy with its original cluster, I mean, you had certain data point, let's say some xk, which was let's say my xk was assigned over here, but let's say my this data point, what we found after finding this new cluster mean, that this data point is more closer to, let's say, the mean of this cluster. If that happens, then I would have to bring this point to the new cluster. Okay, so this is a reassignment step. You are reassigning the data point. So that's why we're saying you have to repeat this step 2 and step 3. So once you find the new means for each of the cluster, again you take each and every data point and calculate their distances from each of the new cluster means. So if any reassignment happens, you do it. And if there is no assignment happening, no reassignment happening, I mean, no data point is moving to, once you reach to that step, when no data point is moving to any of the new cluster, it means you have achieved the convergence, right? So this is, these are the 4 steps that we follow in Lloyd's algorithm. So more formally, what we are saying is, more formal way, I have these data points, x1, x2 up to xn. These are my cluster indicator at any iteration t. So this t is to denote the iteration. So and I know that since if I have k different cluster or k different partitions, then my ZIT, I mean, at any Tth iteration, my Zi will always belong to 1 to k, right? And what is this function? This maps a cluster index to the ith data point in the Tth iteration. At any iteration, you will have, let's say this is my data point and this is my cluster indicator at any iteration. Then you will follow 2 steps here in Lloyd's algorithm. I mean, what we have seen above, there are 4 steps. So the first thing that you would do is you will initialize your ZIs, right? So you will, in the initial iteration, so you will initialize all these, for every data point, you will assign which one is going where, all right? Now, until you converge, so until you converge, you will keep doing these 2 steps. And what are these steps? At every iteration, you will calculate the mean of the cluster. And if in case there is even a single point that for which is not closer to its own cluster mean, then you will have to do the reassignment. It means at t plus 1th iteration, you will find Zi of t plus 1. And this reassignment step where you're finding this Zi at the t plus 1th iteration for the ith data point, right? And this is nothing but you will calculate the distance of each of the data point from the cluster mean it is assigned to, right? And these are the cluster means that I obtained at the tth iteration. That is why when we are updating it, we are saying at the t plus 1th iteration, this is what I should check. I mean, what k I want to minimize this, and I want to know for what k this is happening. So if at the t plus 1th iteration I get, so let's say my xi data point had the cluster indicator of zi, and this zi was, let's say, 2. And if I want to find zi t plus 1, and this is a kth iteration, okay? So if my xi is more closer to, let's say, third cluster mean, then my at t plus 1th iteration, I will get zi to be 3. Right? This is what basically we are saying. Until convergence, you are going to keep doing these steps, and once you reach that stage where no further reassignment is happening, you will stop. And we'll say the solution that we get from there is the solution to our problem. So this is Lloyd's algorithm, and our objective here is to minimize this xi minus mu z zi square, as we had seen previously.
Ma'am,
So
when we reassign a point
yeah,
in a cluster, then
uh,
when we take mean, should we take all the points, like even that was the mean?
can you repeat the question?
Like when we reassignment a new point into a cluster, and
Hmm.
then we take the mean of all the points into that cluster. So we
Hmm.
take mean also, that the mean of that cluster that was before. We take
Uh,
all the points inside that cluster, right?
Correct, correct. No, no. So, see, your mean may not be the value. I mean, you cannot have, let's say, if let's say I have these 1 3 data point, one cluster. I got the mean to be what? 1 plus 3 divided by 2, which is 2. But do I have the point 2 in this data set? No, right?
But
This
let's
is,
say if it is,
hmm.
like sometimes we
If
can
it
get,
is, yes. If it is, then yes, yes, definitely.
okay.
Ma'am, in this reassignment,
Hmm.
xi minus mu tk, in this we consider Euclidean distance, right? And then some.
Euclidean distances.
Okay, ma'am.
I mean, this is
Thank you.
how we have seen in lecture. We'll stick to this. So we'll
Okay, ma'am. And there is,
find
ma'am,
out.
Ma'am, but
Manhattan distance as well. So that is in k means plus plus, or I don't recall
No,
where
see,
we have used it.
if in case the Manhattan distance count, or I mean, it will be explicitly mentioned in the question. I mean, for Lloyd's algorithm, no. I mean, here we are following this. But in case if let's say you get the question where you have to use the Manhattan distance to calculate the distance, because this is just about calculating the distance between the data point and the mean. So in case a question asks you that use the Manhattan distance to compute this distance, then this part will change. Right?
Okay, ma'am. Thank you.
ma'am, in the PYQ and the mock questions, for finding the cluster means for the second iteration, we would not take the last one cluster means for the new one.
In the for the second iteration.
If we have a cluster means first in the first iteration, and if we do the second iteration, then we
Hmm.
calculate the cluster mean for the second iteration, then
Yes.
we could not take the cluster means in the last means for finding the cluster mean for the second iteration.
You're saying okay.
I think,
So
ma'am,
what
he's saying same question someone asked before.
Yeah,
Yes,
Previously.
yes, yes,
that
yes.
previous mean we should take or not.
okay? So
In
what you're saying
PYQ
is
mock,
hmm,
we would not take, then we get the correct answer. But you say take.
no. See, I don't know what is the question. Original question. So the idea is, let's
Let's
say
take them 1 minus 1 and 0.
one, 1 and 0,
1 minus 1 and 0. It's like the mean
one
is
minus
0.
one and 0.
Yeah.
Okay. So 1 minus 1 and 0 is the data point.
And the mean is 0. And the mean is
And
0 for
another
this cluster.
cluster,
Wait. Tell me the first cluster. Yeah. So you're
1
saying
minus
first
1
1.
cluster
0.
is 1 minus 1, 0. Okay.
And mean is 0 for this cluster.
But is 1 minus 1, 0 are the data points?
No, we have the other data points also.
No, can you refer
In
to refer the question to me? Or you
Ma'am,
can
if
put
we
the
take
Hmm.
mean as 1 in this cluster C1, and if we introduce a next another point, let's take an example of 2, then find the new cluster mean for that.
Okay, not understand what I'm trying to say. Do you have the question? Is there any question that you're referring to? Maybe I can look at it and for you.
I don't exactly remember the question, but the thing what we want to ask,
Where did you see this question? Hmm.
Ma'am,
like
Yeah.
ma'am, main confusion is whether if there is mean is making a point, a data point, then it should be taken. If mean is not making a data point, then it should not be taken.
Okay, wait. Maybe I can just take a small example. Let's
This
say
was
I
the
have
only
the data
confusion.
point as okay. So let's say my data point is
So ma'am, I think in
I should
that
have some
question,
example.
in that question, we had some data points and initial means were given, but that
Okay.
was not a data point. It was just a mean, and therefore
Then
we
it
do
should
not
not be taken
include.
in that case.
Yes, but if it was a data point, then we should include.
Yeah, if it was
So
a
there were
data
ma'am
point, then you should include.
yes,
Correct.
but they just gave means that this is your initial cluster mean, so we should not include.
Hold on. Let's see one question so that you get an idea. Um, uh, Maybe this one we can see. Okay, let's say this is my data point. So my first data point is 0, 0. My second data point is 0, 1. All these points are labeled here, okay? You can see the dots and these are the points. Now, suppose I want to use k-means clustering and I take k to be 2. So I want Lloyd's algorithm. I want to perform the Lloyd's algorithm and I want to find, I want to get what is the solution for my original problem. So what we are going to do is, suppose this is my cluster assignment. All right. So this is a randomly chosen. If this is an initialization step, because we're saying we'll initialize our ZIs, right? And we had how many data points? We had 8 data points, right? So my initialization step, which is I assign the first data point to 1 and all the other data point to cluster 2. So this is how it should look like, that my first data point was 0, 0, right? First data point is 0, 0. So this is my first data point. And in the initialization step, what we said is, so Z1, Zi naught is going to be 1 and all the remaining are 2. So this is my initialization step. Now I will calculate the mean of each of the data point from these two clusters, right? So what will I do? This is my one, I have these data points. I have this calculator over here. So these are my data point. So 1, 2, 3, 4, 5, 6, 7, 8. And for all these data points, I know my initial, uh, initialization, I mean, which cluster indicator I'm putting. So only for the first data point, I put it in the first cluster, and remaining all are true, as you can see over here. So what did we say we should do? This is the initialization part. Now, my next step would be that I calculate the mean of each of the data point from these two cluster mean, correct? So since there is only one point which is in plus first cluster, which is 0, 0, so its mean would be just 0, 0, right? So that's what we're doing. We are calculating the difference of each of the data point from the point 0, 0, which is this is my mu1. All right. And next would be I have the remaining 7 data points. So all these 7 data points are in the initialization step. This is in my second cluster. So what I should do, I should know what is the mean of this cluster, right? So once I know the mean of this cluster, so I have this has been calculated, and the mean of that cluster comes out to be 2.57, 1.14. This is my second cluster. I mean, this is my mu2. So now I will go ahead and calculate the distance of each of the data point, the distance of xi from mu1 and mu2. So I looked at 0, 0. If I look at 0, 0 point, I see the difference of 0, 0 from 0, 0. It's just 0. I know this is going to be the smaller one. So what I'm saying is now you just have to assign. So you don't want the exact values to be there. You just want to assign. So here you get it to be 1, right? And why did you say 1? This is zt plus 1. I mean, the second iteration, the next iteration, you will assign 1. I mean, it will go to the first one, right? Yes, Priyanshu.
Ma'am, I'm sorry to interrupt. I got that question. Can I share? I mean, I will dictate. So we were given two initial cluster means.
Can I finish
minus.
this first? Let me
Yeah,
finish this first, and
sure,
then
sure.
okay. So, all right. So for the first data point, I know this is more closer to my 0, 0. So I will assign this in the next iteration. It will assign to 1, right? It will assign to cluster 1. So let's say I have now this cluster 1. I have this cluster 2. So my first data point, my x1 goes to cluster 1. Now 0, 1. I mean, I calculate the distance of 0, 1 from 0, 0 and this. So what we found is that 0, 1 will be more closer to the first cluster. So again, the second data point goes here. Similarly, third data point goes to the first cluster. Fourth data point again goes to the fourth cluster, because the distance of 1, 1 from 0, 0 is 2, and the distance of 1, 1 from 2.57, 1.14 is more than 2. So again, my x4 comes in this cluster 1. Now, if I look at the distance of 3, 1 from first cluster mean or the second cluster mean, I find that this 3 plus 1, which is my x5 point, x5 goes to the second cluster. Similarly, x6 goes to the x7 goes here, and x8 goes here. So now I got all these data point x1, x2, x3, x4 in the first cluster, and x5, x6, x7, x8 in the second cluster. So my next target would be that I calculate the mean of these data point, right? Because this will give me a new mean. So before my mu1 at the 0th iteration, I had gotten it to be 0, 0, and my mu2 at the 0th iteration, I mean the initialization, I had 2.57, 1.14. Now after this reassignment, I will get mu1 at the next iteration, and I will get a new mean at the second iteration, right? So now we'll have to calculate that. So once we calculate that, we got the new mean to be 0.5, 0.5, and 4, 1.5. So this is 0.5, 0.5, and 4 comma 1.5. Right? This is what we got. So again, I mean, now you have this new set of mean in the next iteration. And now again, you will have to do this reassignment. So again, I will calculate the distance of each of the data points from this new cluster indicators and then see if there is any change. If there is, then I will again get a new cluster mean and so on. And this is how we proceed. So you see, I mean, we got mu1 to be a 0.5 pointer somewhere here, and mu2 to be 4, 1.5 somewhere here. I'm looking at this picture. I mean, I can easily say that this is the best I can get. I mean, I don't think there is going to be any reassignment. Even if we perform this step where we calculate the distance of all these xi's, where I varying from 1 to 8 to mu1 and mu2, this new mean, there will not be any change. It will still be the same. It will still be assigned to the same clusters where it was assigned earlier. So this is, I mean, we can see we have reached the convergence. And that is what we are doing it over here. Yes, I think I can take the question that you have put. Priyanshu, is that the question that I put in the group?
Yes,
And in
ma'am.
the
In
chat?
chat window, I have given you the.
Okay.
So we were given 2 initial cluster and we were given the data and we were asked to compute the second iteration and find the mean.
Mm. So initial cluster means are given as -4, 6, 6, right? And the data points are these. So my x1, x2, x3, x4, x5, x6, right? These are my data points. And what is my x1? X1 is -1, 4, 5, 6, -2, -2, 4, 5, -3, -3, and 3, 4. Right? These are my points. And the initial cluster means are given as -4, -4, and 6, 6. So now,
There are 2 clusters.
yeah, I mean, 2 cluster mean it means 2 clusters. So now you have to calculate the distance of this xi from first is distance of xi from -4, -4, and you will have to calculate the distance of xi's from 6, 6. As these are the cluster means. These are the initial cluster means. So if you do this, you will get some value over here. So has anyone solved this? What do you get? So even if I don't solve it, so -1, 4 looks more closer to this one.
Yes, ma'am.
Yes.
So it's a t plus 1. So my this point, I mean, will go to this is my first cluster, this is my second cluster. Let's go to the first cluster. 5, 6 looks more closer to the second cluster mean. So we'll go to the second one. Then third point looks more closer to a first cluster.
First cluster.
Yeah, the first, right? 4, 5 looks more closer to again 6, 6.
Second.
The second cluster. -3, -3 looks more closer to the first one. So this will be my first. And 3, 4 looks more closer to second. So this will be second. So now what I got is, so before my cluster mean, my initial cluster was -4, -4, -4, and 6, 6. So this is my mu1 not part representing the first, initialization, and mu2 not. All right. So now what I got is I have this is my cluster 1 and it's my cluster 2. So in cluster 1, I got the data point -1, 4, -2, -2, and -3, -3. And in cluster 2, I got 5, 6. I got 4, 5. I got 3, 4. Right. So now once this assignment happened in the next iteration, it's in the first iteration. So I will have to calculate the mean of the first one. So what do I get? I get my mu1 at the first iteration is going to be what? It is going to be 4 minus 2 is 2, 2 minus 3 is -1. So -1 divided by 3, and this is -3, -3. So -6 divided by 3, it is -2. So this is my mu1 that is right. That's correct?
Here is the question that that
Mhm.
means the -4 and -4 we won't take.
No, you won't
That was
take.
the
Why will you
question.
take?
That is not the point, should not be taken.
That is not a data point, right? Why should you take
And when
that?
if it is a data point,
Then you should take.
okay.
If let's say if it was given that my mu1 naught, let's say was 4, 5 or -1, 4, or my mu2 naught is -3, -3, then you will have to take, because these are your data points. You cannot do this. I mean, you cannot leave this. So maybe what happens is, in case this is the same, one way to think about it, like, let's say whatever initialization you gave, I mean, for each of these x's, you had some zi naught, right? So maybe something happens like you get some initialization, and for that initialization, you are getting a cluster where the data point, where the data points, where the mean is like coming out to a particular point. So it's okay. I mean, it's not a big deal. So what all you have to care is whatever data points you are given, you should always take those data points. So in this example, you're taking these data points. So you will always calculate the distance of these data points from the means you get. All right. So just take care. Whatever the data point is given, you have to do it. I hope this is clear.
Yes, ma'am.
Ma'am, in this mu1 dash, it will be -2, -3.
-3 is it? 4 minus 2 is 2. 2
4 to
minus
6, 3,
3.
9, 9/3.
No, it's -1/3.
4 minus 2 is 2. 2 minus
But
3
I
is
think first
-1.
was
-1 by 3.
-4. Okay, okay. I think it's
-4.
my mistake. So the data point was -1, minus. I'm sorry. I have actually give you wrong data point. It was -1, -4.
Okay, okay. All right. So accordingly, it will change. Even I thought the
Yeah,
question
yes, ma'am.
might
Yes,
not
ma'am.
get. But yeah. So this is how you can do. You will get a new mean. Now you will find the distance of each data point from this mean. Okay. All right. So we were at Lloyd's algorithm. All right. So we saw what is Lloyd's algorithm, and what we said is um, we can initialize it randomly. That is, we can from all the data points we can just randomly give the zi not values. This is one way to do it. One way to do the initialization, and the other method, other way to do the initialization, or a more proper straightforward way to do the initialization is something which we do using k-means plus plus. So k-means plus plus is a better way to choose your cluster means in the initial step. And once you choose those cluster means, initial cluster mean, you can again follow the same process that has been done for the Lloyd algorithm. So in k-means plus plus, what we did is you don't you don't choose randomly all the clusters initialization. I mean, not all the initialization. You only decide what is going to be your mu1 naught. You only decide your first cluster mean. Randomly choose from the set of data point. You randomly choose one cluster mean. Now, what we want is you want the next cluster mean. You want the next cluster mean in such a way that that cluster is like in a way more far. I mean, it is far from the initial cluster that you have chosen. You want to choose in that way. So to choose it in that way, you would want to give more weightage to the point which is farther from my initial cluster mu1 naught, right? And once this is what we do. So if you have decided your mu1 naught randomly, you have chosen one, and for the next point, you would want it to be that point which is farther. So to get that point, I will give more weightage to that point. All right. So if we give more weightage, it means more chances for the farthest point to be the second cluster mean. And similarly, if you want to choose the T8 cluster mean, give higher weightage to farthest point from the nearest already chosen means. Let's say if you have chosen two means now, it is based on your mu1 naught and mu2 naught. You have chosen your mu2 naught also. Then for mu3 naught, you would want a mean, that cluster mean that is far from these two cluster means. So to do this, I mean to follow this step, what we use is something called that is score. Okay. So once I have decided my mu1 naught, and I want to find my mu2 naught, then I will calculate the score for each of the data point. So how can we calculate this score? Is score of any data point is going to be minimum of so since this is just one that is fixed, so this is going to be minimum of, if I want to find the score of x, that will be distance of x from my mu1 naught. So just write mu j naught here. This is to denote any general mean, and here my j will vary from 1, 2, so on till n minus 1. So if I have k different, so if I have chosen only one cluster so far, this is going to be just distance of x from mu1 naught, because I don't have any other mean on which I would want to take the minimum, right? Because their minimum is just going to be for j is equal to 1, right? Because I have only decided one. So I will calculate the mean. So I will calculate the distance of, this is basically the distance of my x from mu1 naught, square. So any data point. So if you have n data point, x1, x2, so on to xn, then you will calculate the score for each of the data point, score of xi, and that would be just distance of your xi from your mu1 naught square. Right? You calculate the distance, and once you calculate the distance and what is that will be called the score of the data point, then what was my goal? I would want my data point, the second cluster mean to be as far from the first cluster mean, correct? So suppose if I have these data point, and let's say this is my mean, this is my initial mean. This is my mu1 naught. So I will calculate the distance of each of the point from here. Right? This is calculating the distance of maybe one point we can put very far. This is 1 point. So I would want this point to come as the second cluster, I mean, ideally. So to achieve this, what we are going to do is we are going to give this point more weightage. So if the distance is more, I mean, if the score of a data point is more, I would want to give it more weightage. So more weightage as in like you will define a distribution for all these data point. And how will these be given? So suppose you have three data point, which is 1, 2, 3. All right, and you calculated the score for each of these xi, and let's say the score for my data point 1 comes out to be 5. Score of the data point 2 comes out to be 7. Score of 3 comes out to be, let's say, 10. Right? So you define a distribution on this. So how will you give the probabilities? You will give, I mean, the probability that your probability of this data point 1, probability of xi is equal to 1 basically, would be 5 divided by 7, 5, 12, 12, 10, 22. And 7 divided by 22 and 10 divided by 22. So you can see that for the data point 3, so this data point 3, the score of the data point 3 has the maximum score, which is 10. So if I'm saying this data point 3 has the maximum score, it means this point is the farthest one from my mu1 naught, right? The farthest one from mu1 naught. Then ideally I should give it the more weightage. So here you can see that this has more probability of coming as mu2 naught. So this is just the probability. I mean, as compared to these three, I mean, this is, I know this is the highest, but this is just a probability. I don't know if this data point will actually come to my mu2 naught. I mean, but the way we have designed it, I mean, my algorithm should take with higher probability this data point as mu2 naught. That's all we can say. There is no guarantee that this point will be chosen in the second cluster. All right. So this is what we do in k-means plus plus. So this way you can find, let's say, you perform the algorithm and the algorithm chose some point and you get your mu2 naught. All right. Then your task would be to find mu2 naught in case you want three different partition or three different cluster. Then you would also need your mu3 naught. So how can you find the mu3 naught? Again, you will have to calculate the scores. So how are we calculating the scores? So scores, the way we are calculating it is, now you would have minimum of j is equal to 1, 2, because now we have my mu1 naught and mu2 naught. We have these two means. So now to calculate my mu3 naught, I will take min over j varying from 1 to 2. Distance of xi from mu1, mu naught, right? So this will be what? This will be minimum of pi norm of xi. So if I'm calculating score of xi, so min of xi minus mu1 naught plus square time comma distance of xi from mu2 naught square, right? And so whatever is minimum, that I will call it as score. So let's say my algorithm chose this point to be the second, I mean mu2 naught. Then again I will have to calculate the distance of each of the point. So now I will have to calculate distance of this point from mu1 naught and distance of this point from mu2 naught. Okay. So whatever comes out to be minimum, I will call that as the score. Okay. Then I will calculate distance of this point from this and this. I calculate distance of this point from this and this. So you calculate for every data point, you calculate this distance, and whatever is minimum, you call that as your score. So once you have the score, again, you will see whichever score you calculate this for x1, x2, so on till xn. Now, for whatever data point your score is the highest, that will have more weightage to come or more chance to come at your third cluster mean. And that way you can find your U3 not. I mean, you won't find it. I mean, this is just a probabilistic way to do it. So algorithm can choose any of these data point as a U3 not, but the way it is designed, it should choose. I mean, these are the probabilities with which the algorithm should choose your U3 not. So this is another way to initialize. All right. So
Ma'am,
this
will
is.
you take a question on this topic?
Will I take? Yeah, we can take
Ma'am,
questions.
I have
Wait,
pasted the question in the chat box on this topic.
about the three. Okay. A k-means plus plus algorithm of k is equal to 3 was applied to the following three data point. 2 is chosen as the first cluster mean. What will be the second cluster mean? Okay. What will be the second cluster mean? I don't think that should be the question. Are you sure this is the question?
No, ma'am.
Yes,
What
ma'am.
is the third cluster mean is more complicated. Like second is easy, third will be
No, but
com-
you cannot ask the question, what does the second cluster mean? Because all you are getting is the probability distribution of these data point on which can be, which can go to mu or not, mu to not, mu to not. Or you cannot say for sure that that will be your second cluster mean or third cluster mean. Are you sure this is
no,
the
but
correct question?
no, just according to k means plus plus algorithm we can find if it's given
No,
in
you
question.
cannot find. I mean, all you can do is you
Ma'am,
can
there is
give
a
the
ma'am, there is one
probability.
question that which point has the highest probability of being chosen as the second cluster mean?
Now
Choose
that makes sense.
Manhattan distance.
Probability.
Now that makes more sense. Okay. All right. So this, I'll take this question. After that, I'll move to week 4. Okay.
Okay, ma'am.
K means plus plus with k is equal to 3 was applied on the following data point. I think this gets first up here. 2 is chosen as a first cluster mean. So you have 2, 2 as the first cluster mean. Okay. So now what will you do? You will calculate the score. So what is given to you is your mu1
Not
not is equal to 2, 2. Now I want to find mu to not, right? So for mu to not, what will I do? I will calculate the score. So my score of 2, 2. This data point. With distance of 2, 2 from 2, 2, which is 0. Then I will find score of 3,3.
It's 2.
Distances, and I think he is asking for Manhattan.
Yes, it's Manhattan.
Okay, Manhattan distance. No? So how is it defined? So we
Absolute
take
of
the norm,
x2 minus
yeah,
x1
absolute
plus
of xi
absolute of
minus,
y2 minus.
yeah, I mean, you just take, okay, just write it here. So it will be what? It will still be 0, right? It's there.
Yes, ma'am. It's
No.
still 0.
Yes, ma'am. In this
Yes, ma'am.
case,
0 for 2, 2, yes.
So for 3, 3, what it will be? It will be 3
1
minus
plus 1.
2
2.
plus mod of 3 minus 2, which is 1 plus 1,
2,
which is 2. Sorry, 2.
2.
Then
4 is
score
4.
of 4 comma 4. So that will be 4 minus 2 mod, which is 2, 2 plus 2, which is 4. Then I will find score of 10 comma 10. So
16.
that will be 8,
16.
8 plus 8, which is 16. Then I will find score of 12 comma 12.
20.
20.
This is 20, right? Then 13
Yeah.
comma 13.
22.
Last point will have the maximum probability for mean truth.
Correct. And this is 22, right? 13 minus 2, 11. Yeah, correct. So you are saying the point with the highest score has the most probability of getting chosen as the second cluster mean. So what we got is my mu2 naught is 13 comma 13. 13 comma 13, and my mu1 naught was
2, 2.
2, 2.
2 comma 2, right?
Ma'am, but in the
Now
question
I want,
it were mentioned that 10 comma 10 is the mu2 not.
That is a wrong answer.
That
Yesterday it
could
was
be an error
discussed.
actually.
yeah, there must be an error because
Yeah.
Yes,
from
sir.
there you can easily
Yes.
see the probability would be highest for this data point. So
Yes, ma'am.
now your goal is to find mu3 naught.
Mu3. Yes. Then
Right?
it will be
So
again
for
2
that,
comma 2. Can we say that? Like it will be the largest distance.
um, I didn't
Like
understand
it
what
will
you're
be a
saying.
loop if we see it like that.
No, can you repeat what you're saying?
Like if we see largest distance from 13 comma 13 again.
So now you have to do minimum of 2 comma 2 ka distance. You look from 2 to and 13 13. So I know minimum would come out to be 0 only. So this is 0.
Yeah.
Then I will have to do score of 3 comma 3. So that would be what? That would be I will have to look at distance of 3 comma 3 with 2 comma 2 and 3 comma 3 with 13 comma 13. So I know minimum would come with if I take it with respect to 2 comma 2. And that would be 2. So this is 2. Now if I calculate score of 4 comma 4. So again 4 comma 4, I mean if I have to take the minimum distance of 4 comma 4 to this and this. So I know minimum
Till 4.
distance would come with 2, which will be 4. Now score of 10 comma 10. So 10 comma 10 means I know that minimum distance this will give me
Yes,
13.
ma'am.
So
13.
13 minus 10 plus 13 minus 13, 13 minus 10 is 6. Now similarly for 12 comma 12, you will get again this, and this is 2. And for 13 comma 13, so it will be 0. Right? And now what is the question? Is it saying
10,
with the highest
10
number?
will be chosen.
So now 10 comma 10 was chosen, because if you are saying the point with the highest score is chosen, or the point with the highest probability is being chosen as a third cluster mean, then my mu3 naught would be 10 comma
10 comma 10.
So this is your answer.
Yes, ma'am. And that's how we are gonna do in mu4 not mu5 not. So
Yes, exactly. Now let's say there were 4 clusters. So now again you will calculate the score of each of these data points, but now you will have to look at the distance of 2,
Minimum
comma
of these
2,
three.
minimum with which cluster mean you are getting the minimum distance. Whatever it is, you take that and then decide. That's all. Before you were 1, then 2, then 3, then you will go 4, 5, and so on. So if you have k cluster, we'll have to look at k minus 1 clusters. Right. So
Okay,
you,
ma'am.
you see that you don't exactly have to calculate distances. You can just look at the data points, get some idea, plot it, or if it's very obvious, you can just write it. You don't always have to do the calculation.
Yes, right. It's clear now.
One thing that we didn't cover is how do we choose the k, right? So we decide we saw how to solve our original problem where we had to partition our data point in k different cluster, and then we told that okay, we'll use the Lloyd algorithm, which is also called King's algorithm, and this is what we will use to find our final answer. And we also saw the another initialization method, which is King's plus. Now the question is that how do you choose that? I mean, how do you how do you choose how many clusters should you take, right? So the thing is, we want those number of clusters such that your objective function value becomes as low as possible. So this was my objective, right? This was my objective. So what, I mean, what do you think should you take your k to be? The most obvious thing is, like, if I take k to be equal to n, then for sure I'm going to get the least objective value. But is that what we want? No, right? We don't want to make so many clusters. I mean, we don't want each data point to be a cluster. So how do we choose this k? It's a question. So we are going to introduce a penalty term, and this penalty term is what we have to do as p of k. And we'll take this penalty function as some function of k, such that as you increase the number of clusters, this pk also increases. This function should be an increasing function, so that if the algorithm chooses more number of clusters, there is some penalty that you impose on choosing the more number of clusters. I mean, it shouldn't be like you can choose as many clusters you want. If you're choosing more cluster, there is some penalty you will have to pay to choose this. All right. That is why we are saying we'll add this penalty function to our objective function, and then we decide based on that ideal objective plus penalty, whatever this objective plus penalty, right? So whatever k gives you the least value of this, whatever k star can say, whatever k gives you the least value of this objective plus penalty, that k would be say is the most ideal.
Again, how to get that k?
How to get that k? So
If function
think,
is given, we need to derive n equal to 0.
yeah, I mean, you will have some penalty function given to you, and then you will have to do some manipulation way. But I think these sort of questions comes mostly in the coding, where you can design your algorithm and just use the Lloyd and see which k is the most ideal. Doing it by hand is, I mean, ideal is not the good way to do it, but it is more useful than
Just for idea, ma'am, if some penalty function is given,
so
means anyway we need to minimize that, right?
yeah, you would want to minimize that, correct? You want, so it is more like now you want arg min over k, so arg min over xi minus mu zi squared plus pk. So whatever k gives you the minimum value of this, that is the k you choose. Okay. And there are some different ways of choosing this. One is called Bayesian inferential criterion, and one is other is AIC. So all that is not the scope of for this course. Maybe once you go to a higher courses, you can see all that.
Ma'am,
But
we are
this is
doing,
Hmm.
sorry,
Yeah, yeah.
ma'am, we are like starting week 4, right?
We are starting week right after this. Yes,
Okay. So it's the part of week 3.
this is part of week 3. Correct.
Okay. Thank you, ma'am. Go ahead.
Yeah. So one more thing. Yeah. So when you do the Lloyd algorithm, there's one very important step that happens is, I mean, you are able to do it because at every reassignment, your objective function value always reduces. So that is one thing you should keep in mind. If you had seen the proof, I'm not going to do proof over here, but if you have seen the proof, you would have seen that we have proved it there that in Lloyd's algorithm, at every reassignment that we are doing, my objective function strictly reduces. And what do we mean by that? We mean that my f of z1 at t plus 1 iteration, z2 at t plus 1 iteration, so on till zn at t plus 1 iteration should be strictly less than my f of z1 of t. I mean, at t iteration, whatever value you get. So this is you should keep in mind. And that is why we are able to say that my Lloyd's algorithm converges because of this fact. All right. So that was all you had in week 3. Now let's move to week 4 now. Most of the topics I've covered it here. So whatever we have discussed, I would suggest you to work on the problems more now rather than doing the theory, because once you do more problems, you get more clarity on how you should actually do the questions, and that will give you more practice with for the quiz. All right. I mean, I had certain questions for week 4. I want to discuss. Also, let's see if we get time we can do it. But before going to the question, let's look at like small summary for week 4. So in week 4, the topics that we have covered is you have ML estimation, you have Bayesian estimation, you have GMM, and that we will solve using EM algorithm. Right. So, okay. So we'll start with ML estimation. I mean, ML estimation you all would have been very familiar with, as you would have done in this in starts also, even in fact the Bayesian estimation. So the idea is like if you have, if you know that you have observed samples from a certain distribution, then in that case, like let's say if I know that my samples x1, x2 up to xn, they are coming from certain distribution, let's say 50, all right, and these samples are coming in that such a way that they are also independent and they are identically distributed, right? So when we say independent, we mean like let's say if I take the coin toss example, and I'm interested in the head or the take. I'm interested in getting the head. So if in my first toss, let's say I have observed the head, so that occurrence is not going to affect the occurrence that are going to happen on the second sample that I get or the third sample that I get, right? So in a way, all the samples, I will assume that um, they have been observed in such a way that they were independently independent. And the second is ideally distributed. It means that all the samples are coming from the same distribution. It shouldn't be like that my X1 first sample is coming from, let's say, Bernoulli P, and the second sample is coming from some normal with mu and sigma 1, or my X3 should come from some geometric P or something. It shouldn't happen that. So what we want is we want all the samples to come from all the samples should be IIT independent and identically distributed. So this is the assumptions that holds. I mean, this assumption holds. I mean, it is always going to be independent and identically distributed. Now, the idea is you have observed the samples. Let's say I've observed the sample X1, X2, X3, and so on till Xn. And let's say I know something about something more about these samples, where it is coming from. Let's say I know that these samples are coming from my Bernoulli P distribution. All right, but this is all I know, that it's coming from Bernoulli P. But I don't know what P is generating this sample. All right, so in a way, I need to estimate P. So now the goal is to estimate this P. Okay. So to estimate this P, I know that this P can be any value between 0 to 1. It can be. So which P is the most suitable one? Maybe you have observed a particular sample, and from there you come to a conclusion that my P should be maybe should be something, let's say 0.5, or you say that it's a 0.9 or 0.1, anything. But which P is the most ideal one, or which P is in a sense giving you the a proper estimate of which P is the most suitable one? This is the question. So to estimate this, we are going to use the process which is called maximum likelihood estimation. And in maximum likelihood estimation, we are going to first define the likelihood function. So in ML estimate, if let's say I take this example, which is Bernoulli P, I say that my P hat ML is going to be arg of min, arg of max, since maximum likelihood. So you want to have that P that maximizes the likelihood, right? So that maximizes your likelihood. So the likelihood is this, right? So likelihood is given that you have observed. I mean, likelihood is just what is the probability of observing this sample. Okay, so if it was Bernoulli P, I know that my likelihood function for these x's, this is going to be, I define it as product of p to the power xi 1 minus p to the power 1 minus xi. This is my likelihood, right? Sorry, not just this, because I have n data point. So this is my likelihood. Okay, so if this is my likelihood, and now my goal is to maximize this likelihood. So generally, taking the log is much better, right? So because it simplifies your problem. So once you do all that, you take the log and everything, you will get your P hat ML to be number of successes divided by total number of observations. So this is just giving you the number of successes, right? Because since the sample is coming from a Bernoulli P distribution, so I know it can either take the value 0 or 1. That's all. It cannot take anything else. So sum of xi is just going to give you number of successes that you get divided by n. So I would suggest all of you to for some distributions, like very basic one, you should try to remember. I mean, try to remember if you can, like what is the maximum likelihood estimate of some distribution, like what is the maximum likelihood estimation of mu when the samples are coming from a normal distribution with mean mu wherein sigma square. Just sample mean, or the for the Bernoulli or for the exponential. I mean, you can always derive it, but if you can remember, it's much easier, much easier to work with. So, and you already know, even if you don't remember, you always know that how can you find the maximum likelihood estimation? You define the likelihood function, you take the log, you maximize it, and then whatever you get, that is your likelihood. I mean, that is your ML estimation. So for any question that you have for from ML estimation, this is the process that you can follow. If you have any continuous distribution, you just take the product of your effect size, right? So if it is a normal, what will I do? I will take the product of 1 upon sigma under root 2 pi e to the power minus 1 by 2 xi minus mu upon sigma whole square. I is varying from 1 to n, right? So suppose I want to find the ML estimate of mu. So if I want to find the ML estimate of mu, I will treat my x as sigma as constant. Or maybe you can think of it like, suppose your samples are coming from some normal with mean mu, and let's say it is given to you already that sigma is 1. So this also goes away, and all you have to do is to solve for this. And log is always a good way to work with it. So if you take the log, this product goes to summation, and it's simpler. Yes, Sapna. Yeah.
Yeah, ma'am. Ma'am, you were saying to remember some formula. Could you name it or could you tell us, please, once again?
No, very simple one. Like I think Bernoulli and normal are the very simple one, and it comes. It's the application is quite wide for these two. So
Okay, ma'am.
I would not say so. There are various distribution. I would not suggest you to remember, but I think if you have enough practice, you already know what is the answer. So distributions like Bernoulli T, Poisson lambda, exponential lambda.
Sorry, ma'am. What is that second one? Poison?
What is
The second
Poisson?
one.
Yeah,
Poison. Yeah.
yeah, Poisson lambda. Right? I mean, you don't have to do all that. I mean, you just know how can you find the
Yeah.
maximum likelihood estimation.
Y-
That
yeah.
is all. Yeah.
Got it, ma'am.
So this was about the ML estimation. I mean, it's not that you will always be given this likelihood function. I mean this PDF or CDF explicitly. I mean, it's not like it will always some known distribution like Bernoulli, Poisson, exponential, normal. It is not possible. Sometimes you might have questions like you have the samples x1, x2 up to xn, and they are coming from some distribution, some distribution which follows the PDF, certain PDF, and you will some PDF given to you, fx of x, something it can be. Then in that case, instead of this PDF, you just put it here and then solve for it. That's all. Then this is about ML estimation. Then next comes the Bayesian estimation. So in Bayesian estimation, so again, the goal is the same, that I want to estimate my parameter theta, IID. Okay. They are coming from this distribution of theta. The theta is the parameter. So
Excuse me, ma'am.
yeah, yes. Tell me.
Sorry to disturb you. Ma'am, can we do first ML estimation questions so that we'll get an idea?
Okay.
Yeah, please.
see if I have, yeah. This question. So this question says you have, let's say, 300 data points, each of which is either 0 or 1. So the Bernoulli distribution has been used to model this data. And if the MLE estimate for the parameter P is 0.6, then how many zeros does this data set have? Is the question.
120.
Ma'am, is it mean success is given? Right, ma'am? Bernoulli success is given.
Yes.
Okay.
So someone gave 120 as the answer, and this was correct. Okay.
Ma'am, we'll try.
Yes, 120.
Yeah. So why is it that? Because see, you have a hat ML to be number of successes divided by total number of observations. And this is given to you as 0.6. So from here, you can find the number of successes. I mean, the number of times you have observed your fun. So that would be, the number of successes would be 300 times 0.6. That is just 180. So this gives you number of successes. So number of successes are the number of data points with which has 1, and that is 180. So number of zeros would be 300 minus 180 is 120. So for this question, see, if you are able to write this very quickly because you knew what is the HTML. In case you did not know this, then you will first go and calculate. I mean, you find your ML estimate and then you will get this, and then you will substitute. Right? Very simple, right? Then let's say this is my next question. So suppose you have the data point 1, x1, x2, x3, x4, all of which are non-negative, and you are saying that these data points are IID with the following density. Then you have to find the log likelihood of this data set under this distribution. Any guesses what distribution is this?
Exponential.
Exponential.
Exponentials. So what is going to be the log likelihood for this?
Sample minimum.
No, I'm not asking you. I'm asking you log likelihood. How will you do
Ma'am,
it?
9 over some of these data points.
9. No, this is different question.
So there are 9 data sets. Oh, okay, that is different question.
Yeah. So see, likelihood would be what? Likelihood of lambda would be product of my lambda e to the power minus lambda xi. I will vary from 1 to 4 because I have 4 data points. So all I will do is this is going to be lambda to the power 4 e to the power minus lambda x1
X1,
times
X2,
e to the
X4.
power minus lambda x2 e to the power minus lambda x4. So this is what? This is lambda to the power 4 e to the power minus lambda sum over xi. varies varying from 1 to 4. This is my L of lambda. Now, if I have to find log of L of lambda, then it will be 4 times log of lambda minus lambda sum over xi, varies varying from 1 to 4. So this is the log likelihood of the data set. That's right. And now, if let's say you have to find the ML estimation of lambda, then what will you do? You will take the derivative of this, and it will be 4 upon lambda minus sum over xi, I varying from 1 to 4. Then you equate it to 0. And what will you get? You will get lambda to be sum over this is
4 by
just
summation of
probabilities.
4 by summation of I is equal to 1 to 4.
Yeah, 4 upon sum over xi.
What it would be, ma'am?
This one.
Ma'am,
And this
what
is
we are
Exact
nothing
calling?
but
values are
you
not
know
given, I
1
think.
upon values are not given.
Ma'am,
General x1, x2, x3, x4.
what we are calling this lambda LM ML.
Lambda hat ML is maximum likelihood estimation of lambda.
Got it.
So even for geometric, you get the reciprocal of sample mean. This, yeah, it should be, I think, reciprocal of.
Yeah, ma'am, it is reciprocal. That.
Alright. So this is what you can, this is how we can do it.
Ma'am,
Next
approximately
is
how many questions would be there in quiz one?
maybe 12 questions.
Okay, ma'am. In all the previous year question paper, it's close like 16, 17 questions.
16, 17. I really don't remember. I think it should be below 15, I guess.
Okay.
And ma'am, what is that weightage? What do you think, like, of in week 1 to week 4? Is it equal or?
It will be almost equal for all
Yeah.
the weeks. Yeah.
Yes, ma'am. Vishal sir told actually in the last class that it will be
Yeah.
equally weighted.
Yeah. For,
4 questions from each week.
yeah. Yeah. Correct.
Ma'am, actually, in the last term paper I just saw, previous term paper, there are numerical questions like theoretical based, or like sir in this session also I saw that Karthik sir said most of the question would be not that numerical, but theory based, and theoretical question will came. So numerical question based in the paper I saw in the PYQ paper, just previous term of that.
Mhm.
So ma'am, like, is it the same pattern or it's like the mock given?
Um, I have not seen the mock. I am not sure what questions I've got in mock, but okay, let me just check.
Mock questions is already from September 2022 question paper.
Yeah,
That's
it's
okay. I don't worry about the pattern of the questions and all and how many questions. I'm sure the questions are not very difficult. Uh, there will be some questions which are very straightforward. There will be some question where you might need some thing to work on. But
got it.
sure, it's not very difficult paper.
Hello,
Everything
ma'am.
should be. Hmm.
I just want to ask one thing that in point estimate, there is two formulas, expectation of the posterior and mode of the posterior. Is
Hmm.
expectation of the posterior or mean of the posterior is the same Both things are same or different?
You mean expectation or and mode?
No, expected value of the posterior is equals to alpha plus number of success upon alpha plus beta plus total number.
No. So you cannot just rely on uh, one possible example.
No, no,
So
I just
no, I'm
that's
just going to explain Bayesian now, so I'll cover that also. I'll cover your question. I'm just
okay.
starting Bayesian.
Okay.
All right. So in Bayesian estimation, again, our goal is the same. So I have my x1, x2 up to xn, IID, let's say f theta, some distribution these samples are coming from. And again, I want to estimate my theta. But when I'm talking about the maximum likelihood estimation, there I am assuming that my theta is a constant. Theta is unknown for sure. I mean, even here or there, theta is always unknown. But in ML, my theta is a constant, ML estimation. And here my theta is a random variable. So if I'm saying my theta, if I'm assuming that the theta is a random variable, it means my theta will follow certain distribution, right? Let's say theta follows some distribution g of theta. Okay. So, and this is something that I will have to take a call, like what distribution does it follow? What information do you have for the data? What do you think what theta is coming from? Which distribution is it coming from? So this is something which we call it as a prior distribution. Okay. So whatever prior information or your belief you have for the data before even seeing the data is that you should just mention it. And that is what we are calling the prior distribution of data. And once you have the data, I mean, once you have decided what your prior is, and now you are observing the data. You are observing the data, right? So now the data has come to you. So once the data has come to you, now what do you think? What do you think of this data now? Once you have observed the data. So before when you said that your theta is following a certain distribution, it's a g of theta, and this is my prior distribution. Then once you get the data, prior distribution. And once you get the data, you are going to update your probability of theta given the data. So now you have the data, and now what do you think of the distribution of the theta? And this is what we call it as posterior distribution. Okay. So what in Bayesian estimation, your goal is to find this posterior. You want to find this. We want to estimate your theta, right? So you want to estimate the theta, and to estimate this theta, you are going to use the posterior distribution. And posterior distribution turns out to be proportional to the prior distribution times the likelihood function. Likelihood is the same what we have defined in earlier for ML estimation. So once you know what distribution, what is the posterior distribution of your data. So let's say for example, let's say I get my posterior to be a uniform distribution, suppose. Uniform or uniform is not a good choice over here. So let's say beta distribution. Some parameter alpha, some parameter beta, or this is something that can happen. The second is, let's say, just one other example. Maybe the posterior you get is a Bernoulli T distribution. Okay, so this is just some example, maybe just a rough idea. So let's say these are the posterior that you got. Maybe you got posterior beta, you got posterior Bernoulli. Then now you only know the distribution. You know what is the distribution of what is the distribution of your data? What is the posterior distribution of data once you have observed the samples? Then once you know this distribution, now your belief, I mean, now you can estimate your data. So, and how do you estimate it? To estimate this, one very possible, one way to do it is you um, you find the expectation of your posterior distribution. So whatever expectation you get for the posterior distribution, I will say that is my estimate for theta. That will be your estimate of. And the second way is like you find the mode of the posterior distribution. That is called the maximum a posteriori distribution, right? So this maximum a posteriori distribution is nothing but whatever posterior you get. So this is like whatever posterior you get, you want that P that maximizes your posterior. So like in ML estimation, you were finding that parameter, that P, which gives you the maximum likelihood. So in P hat MAP, what you're doing is you want that P that gives you the maximum posterior distribution. And so this is more like mode of the distribution. So these are two ways in which you can estimate your parameter when you're dealing with the Bayesian estimation problem. All right. So this is all we had in Bayesian. Yeah. So the question that you had earlier, what was the question? Is it clear to you, like what we want? I mean, how do we estimate?
Yeah, ma'am, it's clear.
Okay. So we'll see one question again for this. And the question is this. Yeah. So suppose you have the prior, you have the samples coming from Bernoulli P distribution, and the prior information that you have on P is that your P follows a beta distribution with the parameters 3, 2. Now, the data set that you observe, so you have this prior, now you observe this data set, and now you want to find P hat, the point estimate for the parameter with distribution P. What is going to be P hat if you use expectation of the posterior as the estimate? So can you find this? What do you think is the answer for this question?
Ma'am, we'll try.
Yeah. So do you have any other session scheduled at 8?
No,
It was at 6 MLF, but I skipped that
Okay.
session.
Okay. Because I saw many people are gone after in like few
Yes,
minutes.
there might be some other courses.
Mhm.
Because nowadays I think there are several courses which are overlapping.
Okay. All right, just try this question. No, question method.
0.6, ma'am.
0.6. Okay.
Yes, ma'am, 0.6.
Okay. So we all got 0.6. I think that is the right answer.
It would be alpha upon alpha plus beta, which is
Alpha upon alpha plus beta. Yes.
so it would be 3 upon 5.
0.6.
No. Did you take from here?
M11.
0.61.
Sorry?
0.61. No, you said alpha upon alpha plus beta. So you mean 3 upon 3 plus 2, which is 3 upon 5. It is 0.6.
No,
No, it is.
no, ma'am. 11
No,
over
ma'am.
11 plus
11
7.
upon 18.
This is correct. It's correct.
How 11 upon 18?
See, this is the prior.
Likelihood we will have to find.
You need the posterior, right?
Yeah.
So posterior, I told you that it is proportional to prior times likelihood.
Yes.
So now my prior is following a beta distribution with parameter 3, 2. And I know my beta distribution looks like x to the power alpha minus 1, 1 minus x to the power beta minus 1. So x to the power alpha minus 1, it means now my parameter is p. So instead of x, I'll put p. So p to the power alpha minus 1, which is 2, 1 minus p to the power beta minus 1, which is 1. This is my prior distribution. And likelihood. So how many 1 do you have? You have 1,
8.
2, 3, 4, 5, 8. Right? So p to the power 8, you're going to p to the power 8. And 1 minus p to the power. How many zeros do you
5.
have?
5.
1, 2, 3, 4, 5. So 5. So now this is what? This is p to the power 10 and 1 minus p to the power 6. And I know this again looks like a beta distribution. So this is beta x to the power. So beta alpha comma beta, right? So this is going to be 11 comma 7. Now if you find, now the question says beta p hat as a point estimate for the parameter of Bernoulli distribution when we use expectation of posterior as the method of estimation. So now my posterior is beta 11 comma 7. So if I find the expectation of this posterior, I'm going to get 11 upon 11 plus 7, which is 11 upon 18. So this is the posterior. So don't look at the prior and calculate. You should find the posterior, and that is the prior data.
Got it, ma'am.
Yeah. Okay.
So you wrote there that of from beta, we should find the prior of that. I thought you said that it's prior, so that's why I wrote like that.
No. The prior information is given to you that your parameter p,
We
follow,
find it the posterior, right?
you have to find the posterior. Yes.
Got it. Got it.
All right. So after the Bayesian estimation, we have Gaussian mixture model, and for this we are going to introduce the EM algorithm. So what we are saying is, let's say, so before whatever we have seen is your samples are coming from a single distribution. Now what happens if your samples are coming from a mixture of distribution? So for example, what happens if you're, so here we're talking about Gaussian mixture model. So we are saying what happens if your samples are coming from distributions like this. Let's say. So you can see we have three different, three normal distributions, right? So you have this one curve, you have another curve, and this is never going to zero. So, this is one normal, this is another normal, this is another normal. So you have three different normal distributions. So now we are saying, what if your samples are coming from this distribution? Yes. Right. So let's say you have 6 data points, and it was, I mean, it was not at all ideal to say that. And since these samples are, if we're assuming they're coming from a real line, it is not at all ideal to say that these samples are coming from just one distribution, this normal distribution, because that would not. If we are saying that this is coming from a single normal distribution, then in that case we are giving much more weightage to these 2 points, and these 4 points are in the region where the probability is quite less. So this is not what we want. What we are saying is my samples are coming from now mixture of 3 Gaussian. So when this happens, in this case, so you don't have just one parameter or two parameter. So let's say if my question was like my sample x1 to xn, they were coming, let's say, from some normal with mean mu Bayesian sigma score. If that was the case, I know using the ML estimation, I can find my mu, I can find my mu hat ML, I can find my sigma hat ML. I know how to do it. But now here, what you have is your samples are coming from three different distributions, right? So your samples are coming from one normal distribution with mean mu1 comma sigma 1 square, then mean normal with mean mu2 comma sigma 2 square, with mean mu3 comma sigma 3 square. So you have three different normal distribution, and there is a mixture of these three, and the samples is coming from that distribution. So now you have to look at various factors. So you should now you have how many six data point you have. So all this data point, you also have a certain indicator. Like let's say this is my first distribution, this is my second distribution, third distribution. I mean first cluster, second cluster, third cluster, something like that, or first mixture, second mixture, third mixture. Then I know that all these points are coming from my first mixture. All these points are mostly coming from your second mixture. I mean, more probability of this point coming from the second distribution, and this point has more probability of coming from the third distribution. But you can always see that if I look at this data point, so I know that this data point has more chance of coming from the first distribution, but that doesn't deny the fact that it can also come from a second distribution, because it is not, it is never zero, right? It is, I mean, this is your one curve and it is never zero. Even if it's very less, there's still a chance that your this data point, this red color data point, this can come from your second mixture, or it can come from your third mixture also, right? Because this is also, this is never going to go zero. It will be very less. This probability that your this data point will come from the third distribution, third mixture, will be very less, but is never zero. So there are now other factor that is there, and that we'll call it as the probabilities with which this point can come from mixture 1 or mixture 2 or mixture 3. So we'll define something which says like probability that any Zi, so Zi is just the indicator, mixture indicator. So Zi is some mixture L, Zi is coming from some mixture L with probability pi L. Okay. So if we are saying, if I'm calling this point as xi, so I'm saying probability that my Zi is equal to 1 is going to be pi 1. So it means, what is this? This is the probability that my ith data point is coming from mixture 1. And that is pi 1. Then probability that my ith data point is coming from mixture 2, and that is pi 2. And probability that my ith data point is coming from the third mixture is, this is pi 3. So we define this probabilities P of Zi is equal to L as pi, such that there are two conditions over here. So the first condition that it should follow is all these pi i's, I mean, these are nothing but the probabilities, okay? So all these pi i's should always lie between 0 to 1. And the second is that summation of all these pi i's, I varying from 1 to L, or not L, I mean, I will stick to the cluster, since when we're talking about the clustering, we said K clusters, here we'll say K different mixtures. So I varying from 1 to K should be equal to 1. So sum of all the probabilities should be 1. So maybe you can think of it like, let's say my pi 1, since I know this probability is higher, should be higher, of or pi I, right? So pi I would be not pi. I mean, I'm talking about just this data point. So pi 1 should be maybe 0.7, and pi 2 you can take it as maybe 0.2, or pi 3 can be 0.1. So you see, all that should add up to 1, right? Because the probability that this point can come from any of these should add up to 1. So you see that apart from this mu I sigma i's, you also have another component that you will have to estimate, which are these pi i's. So in Gaussian mixture model, when you have this model, when your data set is coming from a distribution like this, then you have the number of parameters that you want to estimate, assuming that you have k mixture, is 3k minus 1. So 3k, why 3k? Because for every mixture you are going to get k number of mu i's and k number of sigma i's. So you will have 2k from here, and now you will have this pi 1, pi 2 up to pi k. So you have pi 1, pi 2, so on till pi k. Right? This is also you have. But I know that, and this is total k. But I know this should add up to 1. So if I know k minus 1 pi i's, then I can explicitly find my kth pi. So that is why we'll have to estimate another k minus 1 parameters. The total number of parameters now that we have to estimate is 3k minus 1. So to solve this, to solve this problem, where you have to, now the parameters that you have to estimate, the parameter space that you have to estimate is, now you have mu1, mu2, so on till mu sigma 1 square, sigma 2 square, so on till sigma k square, and pi 1. You have pi 1, pi 2, pi 2, so on till pi k. Right. So these are the parameters that we have to estimate. So if we go ahead with the maximum likelihood estimation problem, then we are going to get stuck at a point because we are not able to solve the log. So if I will not do the proof and all, I'll just give you what parameters you will get. So if you go ahead and find the likelihood function of your parameters, I know the parameters as theta, given you have all these xi's, given the data point, then you will get something, this will be more like sum over log of sum over pi k of e to the power minus xi minus mu k square upon 2 sigma square k divided by sigma k under root 2 pi, where k is varying from 1 to capital K and I is varying from 1 to 1. So this is using the ML estimation. This is my likelihood function for the GML. But solving this is difficult because you have the yes, Sapna.
Yeah, ma'am. Like in parameters, like as we are saying, this is our log likelihood. Likelihood. For GMM. In parameters, we should add one more parameter, na? Xi to xn.
Those are not parameters, right?
One,
Those are
two.
your data points.
Okay.
These are my data points, right? How can you say this is a parameter?
Yeah,
This is something that you have observed, right? This is not a.
Okay.
So forget the proof and all. So all we are trying to say that we have to estimate these parameters. We have to estimate these parameters. So to estimate these parameters, if I use my general maximum likelihood, it is not going to happen, because when we define a likelihood function, it turns out to be text. Okay, and I know solving this is going to be quite tough, because even though I've added the log, I still have inside the log I have the summation, which is going to be, I mean, you cannot, there is no analytical solution that you can do from here. So to avoid this, so to overcome this challenge, what we're going to do is we are going to introduce some new parameters. We are introducing some new parameters, lambda ik, or yeah, lambda I. Okay. Yeah. So to overcome this, you are going to introduce some new parameters, and these parameters are like for any data point. So for every data point, you are going to introduce. Yes, Priyanshu.
Then this lambda ik parameter, that so is this something has been taken into this course, or is this like across all machine learning courses?
This
I mean,
lambda you're
regardless.
saying?
Yes, ma'am. So
Um,
what I want to understand is that outside IIT as well, if we learn any other courses related to machine learning, so even there, this is how it's being computed, right? Using lambda I, like taking, although notation might be different, but the
yeah. I mean, yeah. So see, I'm not sure about other courses, but there is one course in the degree level, statistical computing, where you do the algorithm, and I mean the process is not exactly the same, but the idea is the same. You do it in just a different way, but this is, I mean, this is how you proceed.
so this is one of the way, right?
This is one of the way to do it. Yes.
Okay, ma'am, thank you.
This is not the only way, but this is one of the way. So yeah, so to solve this problem, we are going to introduce that for every data point, for every I, you are going to introduce this lambda 1i, lambda 2i, up to lambda ki, in such a way, such that if you sum these lambda ki over this k varying from 1 to capital K, it should be 1. So basically, what I'm saying is, if you have, let's say, x1. So for x1, you will have lambda 1i, sorry, lambda 1, 1. You will have lambda 2, 1. So on till lambda k1, because you have k different mixtures. So you will have for every xi, so for x1, you have these. And all of this should add up to 1. Okay. Similarly, you can do for point x2, point x3, so until xn. So now you are introducing, so total number of data points you have is xn. I mean, you have n data points. So for each of these xi's, so if I talk about xn, you will have xn lambda n1, lambda n2, so on to lambda nk. So you introduce these additional terms in your in your algorithm. Okay. So, and what is this? What is this calculating? What is if I take any lambda ki? What is it calculating? Is this is giving you what is the probability that given a data point, if you're given a data point, what is the probability that this data point is coming from some k cluster? So if I, let's say, if I write lambda 2, 1. So this means what is the probability that x1 is coming from second cluster? Sorry, given that you have this x1, what probability is that this is coming from the second cluster? Correct. Second cluster. So this is what we have introduced, and introducing this, how is it going to help us is, now there is something that you can do, and that something is Jensen inequality. So using the Jensen inequality, you can convert this problem into you are going to convert this problem in such a way that you have all this lambda k over here, and the log will have certain value, and you don't have any summation here. Okay, so this is how you will convert. So once you converted it in this fashion, now you can find your the parameters. Now you can find your mu k, sigma square k, and pi k. So to find, I'm not going to go to the proof, skip the proof. So what we are doing is that you first fix your lambdas. Okay. Once you fix your lambdas, then you maximize whatever it is. So if I want mu k, then I will fix my lambda and I will maximize this term, and I will get my mu k. So the mu k that I get, I will just write all these three and all these three terms that I get. So my mu hat k that you're going to get is sum over lambda ki xi divided by sum over lambda ki, where I is varying from 1 to n, I is varying from 1 to n. This is your mu k hat that you should get. The sigma hat, sigma squared hat square k that you get is sum over lambda ki xi minus mu hat k square divided by sum over lambda k I. Right. This is your sigma square k, and your mu k, pi k that you will get is nothing but sum over pi k, where I is varying from 1 to n divided by n. So this is you should know. I mean, so when we introduce these lambda ki's, this method of likelihood that we had seen earlier is now easier to implement. So when you introduce these terms, now you get modified likelihood function. So once you get that modified likelihood function, so the first thing that you will do is you will fix your lambda and you maximize with respect to your theta. So these are the thetas I'm talking about. These are my theta. So maximize with respect to theta. And when we did that, we get these are the estimate for your mu, sigma, and k. Now, once we fix our theta and maximize with respect to lambda, then you get lambda hat k for the data point is some means something like this is a little complicated. So or you don't even have to do this. I mean, you know the exact thing. What you should know is like, what is it that you're trying to find over here? So you are trying to find the probability that Zi is equal to k given the xi. And this is basically, if you use the Bayes theorem, so this is basically xi given Zi is equal to k times probability that Zi is equal to k divided by probability of xi.
Yeah.
Yeah. Yes, tell me. Okay. So these are the so using introducing this, we obtain these we obtain the estimate for these values, parameters. So what the CM algorithm says is you initialize your theta naught. So you initialize your theta naught, which will contain all your mu I naught and sigma square naught and your pi k naught. So you initialize this and until convergence. So as long as your theta t plus 1 minus theta t, when this becomes very small. So we are saying this is the tolerance parameter. So this is the tolerance level that we have set. So we are saying when you reach to a stage when your theta t plus 1 minus theta t is less than epsilon, when the let's say ith iteration and I plus 1th iteration, the parameter values are so close, then we say that we have reached to our we have estimated the parameters. Okay. So until convergence, until you get this, so maybe on the first iteration, this is greater than whatever else is epsilon that you have set. In the second, in the next iteration, maybe still it is greater than epsilon. So you keep doing this, and until you reach the stage where this difference is very small, then we'll say that we have reached our convergence. So this is my first step of the algorithm, and then the second step of the algorithm. And in this, I mean, when you're doing this process, I mean, when you're doing this theta t plus 1 minus theta t1, you're basically what you're doing is you are trying to find your lambda t plus 1 and theta t plus 1. So this lambda t plus 1 is nothing but your arc of, I mean, the arc of max of lambda and whatever the likelihood that we got, right? So whatever likelihood we got. And theta plus 1 is arc of max over theta, whatever likelihood that we had. This is basically what we are doing in the, I mean, in the mid step you can think of. And we are trying to check this. So all this thing, theory, it's quite difficult to deal with. But once you code, you will be able to see what is happening. I mean, how is this and this coming inside the code, and how are you checking this and everything. I'm sure you would have some coding design on this. So why is it called EM algorithm is because this is this lambda step that you're seeing here. This is called the expectation step. So we have not seen in this course why is this called the expectation step, but this turns out to be expectation step, and you are trying to maximize this expectation step, and here you are doing it. Maximization step. So you're trying to maximize this expectation, and that's why we call it as EM algorithm. And then once you reach here, the algorithm ends. Correct. So this was about the EM algorithm.
What are these last two statements in brackets?
In brackets here.
Yes, ma'am.
No. So this was the likelihood function that we had. Whatever we had given before.
We can say that like the modified likelihood.
Modified likelihood, yes. Yeah, I mean, in the exercise we have said modified likelihood.
Yeah.
Okay, after applying this inequality.
After introducing this epsilon lambda.
Okay. All right.
Okay, let's do one question from EM algorithm, and then we can close the session. Let's do this. So you have to find the maximum likelihood estimate for the mean of the Gaussian distribution that generates the following data. So this is the data that you have observed, and we are saying as consider a Gaussian mixture model. Sorry. This is not Gaussian. This is the question. Sorry. So you have a Gaussian mixture model, and we are saying you have two components. So you have something like it's this. So mu10 is given to you as 0. Mu2 is given to you as 1. Sigma 1 square is 1. So sigma 1 square is equal to 1. This isn't very ideal, but okay. Sigma 2 square is 2. Pi 1 is 0.4 and pi 2 is 0.6. This is given to you for some data point. Now the question is, what is the probability that the point 1.2 comes from the first component? This is what you have to calculate. So you don't have to do the calculations. I mean, most of the you have to use this table basically to avoid certain calculations. Can you try this? Let me know once you get some answer.
Um, 0.31.
0.31.
Yes, ma'am.
Okay. Anyone else? Okay, let's do this question. Let's see if that's correct. So what you have to find is what is the probability that the point 1.2 comes from the first component. You have to find the probability that my set is equal to point. Okay, someone else also got 0.31. So what is the probability that z is equal to for 1 given that x is equal to 1.2? Right, this is what you have to find. So you will have to use the base rule over here. And what is this? This is going to be the probability that x is equal to 1.2 given that z is equal to 1 times pi 1, right? This will be pi 1 divided by probability of x is equal to 1.2. It means probability that x is equal to 1.2 given that z is equal to 1 times pi 1 plus probability that x is equal to 1.2 given that z is equal to 2 times pi 2. So I know that, I mean, it is given to us here that my pi 1 is 0.4, is 0.4. And if the value is coming from the first component, it means if it's coming from here, so I know this follows a normal distribution with mean 0 and variance 1. So mean 0, variance 1, I know this value is going to give me 0.194. Sorry. Yeah, 0.194, right? Because that's also 50, right? So this is 0.194 into 0.4 divided by 0.9194 into 0.4 plus, what is this? This is what is the, you know that this z is equal to 2. It means the data point is coming from, if the data point is coming from the second mixture, what is the probability of the occurrence of this point 1.2? So this is coming from the second mixture. It means this is coming from a distribution with mean 1 and variance 2. So this holds. So this is going to be 0.279 times 0.6 because pi 2 is 0.6. And if you solve it, you should get point. Is it coming to 0.31?
Ma'am, can you please explain how do we get mean 1 variance 2? I mean, why do we take this last row mean 1 variance 2?
Why do we take which one? Mean 1 variance 2?
Yes, ma'am, just 0.279.
Because it is given that it is a second mixture. So if it is second mixture, what is the probability of 1? The point 1 by 2.
Okay,
So
ma'am,
I
I think
know,
in here at the top it is given, right?
yeah,
Mean 2 is equal to 1, and okay, ma'am, understood. Thank you.
yes. So mean 1 and sigma 2. Right? So 0.279.
Ma'am, in the question paper, these value will be given, or do we have to compute like this table?
Ideally, it should be given. I mean, if or it may not also be given. I can't say for sure. But I'm sure in the paper there won't be much calculation.
Okay, ma'am, because if it's not given, then it will be too much to compute.
Yeah, that's correct. So you get by. So this is correct. So 0.31 is the right answer. Okay. All right. So this is one problem. Let's look at. Okay. We can look at this maybe. So we have a data set with 10 points and a Gaussian mixture model with k components. So now if we fix your lambda and maximize with respect to theta, what is the estimate that you get for mean of the kth component? So basically you want what is mu k hat. Okay. So as we have seen, this mu k hat is nothing but the weighted mean of the data points. Oh, this is just this one. This should be correct. I know this is not sample mean, so this is wrong. I know it is not the mean of the end data point, so this is also wrong. And A is saying it's the weighted mean of the data points, but the weight for the ith component k is given by this. So this is basically what option B is saying. So option A is also correct. This is just straight from your theory. Then one more question that we have here is a Gaussian mixture model is fit for data set with 5 points, and at some time period in the EM algorithm, the values that you got for lambda ki's are for all the 5 points is lambda k1 to 0.9, 0.8, 0.7, 0.6, 0.5. So now you have to find the estimate of pi k after the m step. So you're fixing your lambda, so and you have to estimate your pi k. So what did we have? What we had as pi k?
0.7.
Sorry.
Ma'am, 0.7. Summation of this point divided by 5.
7. Yeah. So we had seen it is just pi k was just adding all these lambda ki for the data points divided by total number of points. So I have total number of points to be 5. So this is just you add everything and you divide by 5, right? Because 9 is 17, 17, 21,
3.5.
27. Okay, 3. Yeah, so these were some questions that I have with me. That's all about week 3 and week 4.